remaining technical problems that we introduced the speaker already, so we don't cut too much listeners' time. I'm very happy to have Rien van der Weinhardt here. He's a cosmologist from the University of Groningen, professor in Groningen. He has an interest not only in cosmological problems, but also in computational chemistry and questions of pattern recognition, which makes him a perfect speaker for our conference here. So he's not a core AISTATS person, but he brings something very interesting to this community, and also it fits very well to this place that we work at, La Palma, the biggest optical telescope currently in the world. So we're very happy to have Rien here with us today.
Thank you very much. First of all, I'm quite honored to have gotten this invitation, and it was a great pleasure to accept it. And I've been learning a great deal, I must say, over the past few days. So I'm not an expert in machine learning whatsoever, but I hope that in the coming hour I will sort of convey to you the sense of problems that we are dealing with in cosmology. In particular, when we turn towards studying the large-scale distribution of galaxies and matter. And large-scale, I mean, we are talking about distances of hundreds of millions of light years down to tens of millions of light years. I will try most of the time to keep in mind that I should tell to you light years, but it may be a professional mistake that I usually say parsecs, because astronomers have this very funny unit of talking about parsecs. When I say parsecs, just think that parsecs is around 3 light years, and light years is the distance that light travels in let me see. Oh yeah, it works. Okay, that's what I need to test. The work that I will be describing is part of a large project that has many different branches. One of the branches that I will try to focus on towards the end was touched upon yesterday already in a very fine talk, and that concerned homology. It was a great surprise for me to know that some other people also had this interest, because it's only recently that it got into the field of cosmology. But before I will do that, I will try to sketch you the picture of why we are interested in this. So I will take a great deal of your time by something that is not connected to this conference, just sort of paint you the background of the picture. Now, what we are talking about is the distribution of matter on scales of tens to hundreds of millions of light years. If the contrast would be slightly more like on the screen, you would see that the pattern, what you see over there, has a distinct web-like structure. This is a 3D rendering of a computer model of the formation of structure in the universe as we think it has proceeded over the last 13.7 billion years. When you look at that distribution, you see it fails to have a lot of regularity. It is marked by filaments, walls, and the filaments and the walls connect at high density compact nodes, which we know are clusters of galaxies. I will show you soon a picture of that. And it pervades the whole of the visible universe. Another factor that is of importance is that this structure doesn't have one scale, it has a whole range of scales. This makes it notoriously difficult to analyze it. In fact, astronomers have failed for quite some time to analyze it, because astronomers only have one geometry of importance, and that's a sphere. If you look at their theories, it's always a sphere, because that's easy to calculate. So this was quite a challenge to analyze, and that's what I will try to tell in the coming hour, that because geometry and topology has given us some tools that will give us a means of analyzing this. That 3D picture is nicer, but to give a better view, it might be better to give, again, a 2D impression of what this is about. So this is a similar kind of n-body simulation. It's still the imaginary world of the theorists. And what you see over here is a slice through a three-dimensional box in which the distribution of matter in the universe is depicted. Now, this is what cosmologists call dark matter. Before I proceed, I should perhaps tell that the universe consists of several kinds of energy. The energy or the matter that we consist of is just a minor part of the rest, at most 4%. Stars are less than 0.1% of the energy content of the universe. So, coming back to the issue of cosmologists versus astronomers, astronomers are studying the stars, and we study as cosmologists more than the stars. We study the 100% that is left. 23% of the matter content of the universe, or the energy content, is so-called dark matter. Dark matter is matter that is not like the atoms in our body. It is an unknown species of matter. We know it's there, because if it wouldn't be there, we would not be there. It exerts gravity, gravitational pull, and because of that, it's responsible for the formation of structure. Right? That's what the theorists are usually depicting. The rest, the dominant part of the universe, consists of 73% of what we call dark energy. Dark energy, we have even less of a clue what it is. We only know it's there since 13 years because we found that the universe is not only expanding, but its expansion is accelerating, which is strange. It's like there is a repulsive medium in the universe, which we call dark energy, and it causes this accelerated expansion. It was last year's Nobel Prize in Physics, or the last year's Nobel Prize in Physics was awarded to the guys who were leading the discovery groups of this dark energy. Up till that point, physicists didn't have a clue that the majority of energy in the universe consisted of this, and we still don't know what it is. Actually, it's perhaps the most important question we have at the moment in cosmology. Now, what you see here is the distribution of matter. We think that this dark matter sort of paved the alleys and the streets in the universe in which finally the gas fell, and the gas basically in the end formed stars and galaxies. So when we are looking later on at galaxies and stars, the stuff that we know and that we see in the sky, you have to remember it's just the light bulbs in a sea of matter, of dominant matter. Okay? Now what you see over here is this cosmic web. And you see this cosmic web has these filamentary patterns, these walls, like you see here, that are actually have as boundaries these filaments. These filaments connect to these very high density nodes, compact clusters, in a network that really pervades the whole of the universe. And here you see some of these little elements. Now, why is this so important? Now, this structure, this cosmic web, finds itself exactly at the transition point where it emerges from the initial conditions in the universe, like it was very much in the initial conditions, towards a state of maturity. That transition state means that you see structure, so you can study here these non-trivial patterns, but at the same time it's close enough to the initial conditions that we can connect them and hope to learn something about the state of the universe in general. Right? So it finds itself exactly at the right stage of study. So it's quite interesting. Moreover, one of the things that we are learning at the moment, and one of the other big questions, is how do galaxies form in the universe? And this is one of the main unsolved issues because it's much, much more complex than what I will talk about today. But one of the things that we are learning is that environment, that is, whether they live in filaments or in these high density nodes or in large empty regions, the voids, is very important. And here we have need a precise way of characterizing this environment, right? So that's what we do. Now let me skip this because that's the program that we should do. Now, up till now, I was sort of painting the fictitious world of the theorists, because I'm myself a theorist, but let me show you some pictures of what we are talking about. This is a typical galaxy, a very beautiful galaxy actually. This is a typical disk galaxy. We think our Milky Way is something like this too. So on a very clear night out here, we go out of the towns, and when you look at the sky, you see this beautiful band on the sky, and you have to imagine that we are sort of with our sun circling around here, around 30,000 light years from the center, and such a disk of galaxies contains around 100 to 200 billion stars. Of these things, there are some 100 billion within the visible universe, right? So there are quite a lot of stars in the universe. They come in all kinds of shades and shapes, although most of them are, most of the bright ones are these very beautiful disks. This I find one of the most spectacular depictions. All of these very beautiful pictures are, of course, from the Hubble Space Telescope. That is provided us over the past 20 years with most of the spectacular movies. So you see here very nicely the core of such a galaxy, and you see these beautiful spiral arms around them. You know, the stars in here, like our sun, rotates in around 220 million years around the center of a galaxy, right? So if you imagine that the last time we were around at the same position, the dinosaurs were not there yet. That's the kind of timescales we're talking about. These galaxies don't like to be alone. They cluster, and they form all kinds of patterns. They cluster because of gravity, and sometimes they collide. Also, that is a very important part of the process of building up of these galaxies. And here you see a minor galaxy colliding with one of these massive disks, and you see they are basically ripping themselves apart. In the end, they will merge, slinging out the gas, and what will remain is something of a galaxy that looks like a rugby ball, an elliptical galaxy. Probably this is going to happen too to us in around 5 billion years. All the indications are that our galaxy is going to collide with the Andromeda galaxy, the big neighbor next door. You don't have to be afraid. The stars won't collide, so it will just be beautiful fireworks on the sky. So don't rush to the insurance company. They group into even larger agglomerations, so now and then. So here you see a picture of one of what in the former pictures of the dark matter distribution was one of these compact dense nodes. This is a picture of the core of one of these compact dense nodes. This is the Hercules cluster. It's pretty nearby, only a couple of tens of millions of light years away. That's pretty close by for us. And you see it's quite a virulent environment over there. You see the galaxies are colliding with each other all the time because the density there is at least 1,000 times the average in the universe. So these are really hot regions with a lot of interaction. These clusters are very important because they are the most massive and most recently fully collapsed objects in the universe. That is, they are the most massive objects that are individuals. The cosmic web itself is not an individual. It's basically an outline of a structure, but you cannot say, like, you know, this individual is this filament. With a cluster you can, right? So Hercules cluster is a real object. So that's important to keep in mind. Now, what cosmologists have been doing over the past 25 to 30 years is trying to make a map of the distribution of galaxies. Now, remember that I'm saying the distribution of galaxies. We have the hope that these galaxies trace the underlying dark matter distribution. We're not sure. It's only now via other techniques that we are getting hold of that. So the hope is that the galaxies sort of trace this structure. This was one of the earliest attempts in the 1980s, very revolutionary. So what they did is on a small region of the sky, and here you see each of the points is one of these huge galaxies. Right? So for the cosmologist, a galaxy has been degraded to just a point. And we are looking at the distribution of these points. And you see it's quite irregular when you look on the sky. When we finally managed to measure the distances in multitudes of each of these galaxies by measuring actually the velocity with which they recede from us, and the velocity is related to the distance because of the expanding universe, we got a surprise. Here you see sort of the first depiction, when I was a beginning student, I remember that in 1986, this was a total surprise. We had expected that these galaxies would be distributed randomly through the local volume, with only so here and there some clusters, like here. It turned out actually, when you look better, that there were large empty regions, and when you look well here, you see a kind of a filamentary extension and a filamentary extension here and there. That was the first realization that our universe was marked by a non-trivial, complex spatial pattern. But we had no clue of how to analyze this or how to describe this. And for 10 to 15 years, cosmologists basically said, once they accepted this, it looks like a web, or this looks like a filament. That was all they could do. There was no numbers, so we couldn't use it to measure anything. Right? Nowadays, we are on much bigger terms. Here you see a part of the sky by the so-called Sloan Digital Sky Survey, the largest mapping effort in astronomy of the distribution of galaxies in the nearby universe. Here you see the region of the sky that has been covered. It's more than 25% of the complete sky has been covered. This is the region on the sky. And of each of the galaxies in that region on the sky, the distance has been measured. Right? Out to distances of more than hundreds of millions of light years. Now also in the other region of the sky we are busy. There is an extension towards the southern hemisphere. As you know, there is a difference between the northern hemisphere and the southern hemisphere. So you need also telescopes on the southern hemisphere to do this. And gradually we are building up a very good impression of what the local universe looks like. By now we have more than the distances and the locations of more than 1 million galaxies. This is the way it looks like. Here you see a little bit of an artist impression, but each of the galaxies really observed, and when you map them you see beautifully here a beautiful filament in the distribution of galaxies. So they really exist. And this is a slice through this mapping effort of the Sloan Digital Sky Survey. So it's a two-dimensional pie through this whole three-dimensional neighborhood. And what you see is by now this impression of a web is really totally confirmed. This is real. This is the real world. We ourselves are here at the center, not because we are at the center of the universe, but basically the observational item. From here we are looking outward, and here you see the position in depth, and that's sort of the position on the sky. And you see how beautiful these patterns are, and how intricate. This by now is the largest structure we know of in the universe, and it goes by the poetic name of the Sloan Great Wall. Each time we are looking further, actually over the past 25 years, they found first the Great Wall, and then it became ever greater, and now, of course, running out of names, they had to call it just the Sloan Great Wall. So this thing is around 300 million light years long. Pretty big thing. Now, the question is, where did this come from and why is this interesting? We think that the early universe looked like this. And we not only think, this is a real observation. Turned inside out. When we look at the sky, and we look around 13.7 billion light years further on, we actually hit the surface, and we're looking at the distance, we're receiving light from the epoch when the universe was 389,000 years old, only. At that time, it went through a transition, and suddenly the universe became transparent. That was for the first time we could see the structure of the universe. The radiation that is coming from that epoch was discovered in 1965, and at the time it was sort of only a signal coming from the sky. But since 1992 we are able to measure very precisely the temperature of the radiation as a function of position on the sky. Here you see a map from the WMAP satellite where you see the fluctuations in temperature. The fluctuations themselves are not larger than 1 in 100,000th Kelvin, 10 to the minus 5. Try to measure a temperature to 10 to the minus 5. What you see here, and these temperature differences are a direct reflection of the density fluctuations at that time. And so what you see is this. This is the baby photo of the universe. All the structure that you see in here is in the end evolving in the structures that we see in the map, like the Sloan Digital Sky Survey. Totally amazing to think of this. When you think this about when this structure was actually born, it was imprinted around 10 to the minus 36 seconds after the Big Bang. So when you really want to push it, this is even more amazing. Out of these structures, for example red, the density is slightly higher, so you expect that there the gravity is slightly stronger than average. That means that matter starts to pull there, and because matter then accumulates, it pulls even further, and what you get in the end is a complete collapse of structures. Yeah, here you see a depiction of that. Here you see a high density region, and you see that the matter streams towards these high density regions, evacuates the low density regions, and in the end you see you get very nicely something that looks like a web. So that's sort of kind of the idea that we have is happening. Right? Now, the thing that we can observe from this web is that you see from the last picture, you saw that the collapse, the way the structures are forming, is not spherical. It's very anisotropic. So it's logical that it collapses into filamentary and wall-like features. If you look well, and I will show it later on too, you see that there is structure on a huge range of scales. There's a huge dynamic range, which complicates things very much because it prevents us from taking one particular scale. And we saw that there is an asymmetry between the low density areas, which are becoming the empty regions, and the high density areas, which are the filaments and the clusters and those kind of things. So with respect to the hierarchical structure, here you see, for example, a model, a cosmological model, and we zoom in here on the structure, and you see that at every scale there is this web-like features to describe it. I should show. Oh, how do I play here the movie? Do you know how to push the button on this one?
Is there sound on it?
No, there's no sound, and it goes pretty fast. Okay, It doesn't play? No, then forget about it. Then we just continue. That's too bad, but okay. Now, one of the important questions that we have is, how do we relate this to cosmology? Now, for cosmology, the important imprint is the amplitude of the fluctuations in the early universe, and basically of the amplitude of what you saw of the map of the cosmic microwave background. This is what we call the power spectrum. The power spectrum is a description of the fluctuations on the various scales. For the cosmologist, it's so important because that contains all the cosmological information we have. It contains the imprint of processes that happened even 10 to the minus 36 seconds after the Big Bang. It contains information about how much matter there is, how much dark energy there is, and a whole range of cosmological parameters. The fact that I can tell you that the universe is 13.7 billion years old is because of we are able to sort of mine the information that we see in these maps and extract it in terms of a power spectrum. But we don't have all the details of the power spectrum. So that's the hunt for. Can we decide the various disguises of the power spectrum? So for example, here you have, as a function of spatial frequency, the power spectrum for a range of possible models of the cosmology, of the underlying cosmology. Now, the thing that we are after is to see whether we can infer some extra information from the cosmic web. Basically, we are then mining the stuff over here, around the peak in the power spectrum. That's where we are looking at the moment, and slightly downward. So, if you look well, and here you can't see it exactly, but if you compare it to the former picture, you clearly see there is a difference in the kind of patterns that are emerging between the different models. This has much longer and much stronger filaments than the one previously. You would see it even more clearly when you would compare the outcome in terms of the objects that are forming. So here you see that same model. This was the previous one, this was the one of a couple of slides earlier, and you see in yellow basically outlined the filaments and the strength of the filaments, the amount of mass that is inside, as well as the objects, which here are indicated by circles with the size of the circle proportional to the amount of mass. And you clearly see there's a huge difference between the emerging web-like structures. This is theory. Now comes the question how to get this, how to mine this information. What kind of tools? Now, I already told you about the complications. The complications are, this is a non-trivial structure, it's asymmetric, it doesn't have a preferred scale. So where do we have to go? You know, how to start about this? It's what we call definitively non-Gaussian, and for example, cosmologists like very much to express things only in terms of the two-point correlation function, but that doesn't suffice to describe this structure. I will soon show you. The structures are very complex, there's a wide range of densities, it's a challenge to basically get this stuff out. I always have to explain to my colleagues why this doesn't suffice, because a large amount of effort over the past 30 years has been invested in measuring the distribution of galaxies in terms of the two-point correlation function. And then you tell them, yeah, but that doesn't tell you everything, right? And they say, yeah, but you know, most of the structure comes out okay. Well, here this two-point correlation function, which is, this is the real one measured, and it basically tells you, you know, what the distribution is of the clustering strength as a function of distance between the galaxies. And this is the one that is measured actually from the Sloan Digital Sky Survey. So what we then always show is that, okay, take this model that sort of is a toy model of a spatial distribution that looks like a web. Take its two-point correlation function and then basically randomize its Fourier phases and go back. So you're guaranteed to have exactly the same power spectrum and therefore exactly the same two-point correlation function. That's this. So these two guys have exactly the same power spectrum and two-point correlation function, and they look slightly different. Right? So this is not going to work. That's clear. So we need something else. So this is where we get to geometry and topology. The first thing that we have to take into account is that we are measuring maps by means of discrete objects. So discrete objects is, for example, the distribution of galaxies, or when we look at these large computer experiments of the evolution of structure, it's usually particles. In those cases, we're by now usually talking about tens of billions to the largest one is now going over 100 billion particles. That's the kind of stuff we're talking about. Out of this, we want to extract these patterns, these web-like patterns, in a way that we can extract information. So the first question is how to do this without the more conventional approach of just putting on some filter. Some filter meant, you know, the standard was take a Gaussian filter of some scale, smooth the density field and try to measure what the fluctuations are, or something like that. But I told you, the cosmic web is a multi-scale structure. So by filtering with a priori defined scale, you're losing a lot of your information. Moreover, when you take a spherical filter, well, you don't know a priori the shape of these things, you're basically washing out all the information on the anisotropy. So that's not going to work. It turns out that actually there is a more natural way of thinking about this, and this brought us to the field of computational geometry, where basically you use the information of the so-called Voronoi and Delaunay tessellations to trace the underlying meta distribution. You use the sensitivity of these tessellations to the local density and the local shape to outline the cosmic web. So that's the first thing that we did. Here you see a depiction of a Voronoi tessellation, and a Voronoi tessellation, for those I guess most people know, but let me just tell you, you basically take these points are the galaxies, and you sort of do a divide and conquer, and you basically outline those regions of space that are closer to that point than to any of the others. And in the case of 2D, you get these polygonal cells. And you see, of course, that when the density is higher, locally, like here, you have a smaller cell. So that's an indication for the local density. Its dual, the Delaunay tessellation, is a totally natural grid for interpolating, totally adaptive. So here you connect the points. For example, here, these 3 points share this Voronoi vertex, and actually when you look at them, you find that the circumscribing circle or sphere in 3D is empty. So it's completely uniquely determined. If you have the Delaunay tessellation, you can delineate the Voronoi tessellation and the other way around. When you put this on top of a filamentary distribution of particles like this one, and you take, for example, the Delaunay tessellation, you get this here. And what you see is that in the low density regions, the cells are much larger than in the high density regions. Moreover, you can clearly recognize the filaments in this structure. If you zoom in, you see not only that you find these filamentary patterns, but you also clearly see the nodes, the substructure in this whole region. And you can zoom in even more, and you see really the substructure, the clumps of this whole feature. So by taking these tessellations from the galaxy distribution, you basically retain the whole hierarchical buildup of structure, as well as the filamentary patterns. Now this made us, or prodded us to basically define a method which from this fact was able to reconstruct a density map which we can then subsequently use for all kinds of analysis. So we use the volumes of the Voronoi cells, or of the contiguous Voronoi cells, and the inverse thereof as an estimate of the density. So at each of the points we estimate the density, and then we use the Delaunay grid to subsequently define this throughout space by a simple linear piecewise interpolation on the Delaunay grid. Right? What you then get, is this one lost? Oh. What you then get is something like this, and you see that this structure actually retains the underlying point distribution. We do get the filaments, and we do get them on a range of scales. We do get the voids, and we even find the substructure in the voids. We can find the connections. So geometry here is a great help. It has helped a lot. For those of you who are interested, you can get actually the code for this kind of game. There's now a C++ code which one of my students made, and it's completely user-friendly for the first time, because when it was my code it was a hodgepodge. So you can just test it, right? So not only does it calculate the densities, but it at the same time, and that's very important for our study of the dynamics, can make the velocity distribution throughout the same volume. And for physics, that's very important, to be able not only to tell the structures, but also to tell how they are forming and what the connecting velocities are. And also that, you see, it very nicely allows you to study the dynamics around the various filaments. Now we have this starting point. We can try to see whether we can quantify various aspects of the meta distribution. There's a whole range of tools that we have made. One of them is, for example, an automatic method to trace out the filaments, to take them out and see how they're connected, what their mass is, what their connectivity is, what the connection is towards the different nodes, and all these kind of things. That's called Nexus, and there's another method, Spine, so we can do this. We can also turn towards the low density regions, which is also interesting by itself, and for that we use basically the good old Watershed transform, which is applied to this dt of E density field, and then we get the voids. And what specifically I wanted to work towards is to look at the topology and in terms of the homology of the resulting mass distribution. Now, let me. So the Nexus method is the method that allows us, on the basis of the dt of E density field, to delineate the various structures that are in this map. We do this by means of a scale space analysis on the basis of a method that was basically devised explicitly for medical purposes. Right? You take an image, an X-ray image or whatever, and medical people want to know whether they see a lump or they only see some healthy veins or something like that, and on what scale. And people like Florak, etc., defined a method on the basis of this, and we sort of adapted this method towards our cosmic web maps. So what we basically do is take that map and smooth it, filter it on a whole range of scales, adding another dimension basically. And then we get a four-dimensional map, and from this four-dimensional map we then, with several with a filter bank, we sort of select at each location whether locally the distribution is filamentary or cluster-like or wall-like, and in this way we, in the end, obtain a map where we clearly see here we have a wall on this scale, and there we have a filament, and here's this connection. So you get something that looks like this. This is, again, this is a theoretical model. This is the density distribution. In red, here you see, I don't know why. It was a bad choice to take red and green. We should have known that. It's a lot of people who can't see that. But you see, in red, you see here nodes. And there are various versions of the nexus method that basically focus on different aspects. This was the original method. It sort of got the filaments and the nodes, but it was not that good. This looks a lot better. And here in green, you see the walls. Blue is some clusters, and red you see the filaments. And here you clearly see that they dragged out. Now this is the large-scale pattern. If you are interested in the sort of the substructure of these filaments, etc., you work in terms of the logarithm of the density, and you get a finer grid like that. And this tool at the moment is being implemented to study this intricate network of filaments. That's one particular aspect. The other one is watershed segmentation, where I show you here, for example, a map that was made with DTFE, and in the map we sort of outline the different regions around sort of the valleys in the mountain landscape. And what is blue here is regions that have a density lower than average, and they are the so-called voids in the density distribution. In red you see sort of the outline of the boundaries. So this sort of gives you a cellular distribution and gives you a chance to sort of tell where the void regions are and see which galaxies, for example, are living in these low density regions, whether their properties differ from the rest or not. So that's another way to go. Now, when we've seen these structures, one of the other aspects, of course, is the overall connectivity of these structures. And that brings us to the topic of topology. So the topological analysis of the cosmic web. So that's what today I also wanted to talk about. And in cosmology, there had already been attempts towards studying topology. When in cosmology you say that you are studying the topology of the large-scale structure of the universe, they are usually talking about the genus. And that's around it. The genus of isodensity surfaces. That was suggested in 1986 for the first time by Richard Gott, and has since then been a kind of a general tool to use. But in the end, it's only one number. And that's certainly not the whole story for cosmology or for topology. In addition to that, there were a couple of other suggestions for other kinds of quantifications of the topology in conjunction with the geometry in terms of the Minkowski functionals, which are basically telling about volume of isodensity areas, the surface areas, integrated mean curvature, and the Euler characteristic. These two aspects are certainly interesting, but they are not one consistent framework. So to study this, we are following a slightly different way, and yesterday we heard about it already. Now, why would topology be interesting for cosmologists? Now, the precise location and geometry of the various structures is one aspect. But sometimes we want to measure certain points or certain factors that are independent of a range of distortions that are possible within the distribution of matter, be it artificial or be it dynamic. Like what you see here, here is an isodensity surface, and when you actually deform it in all kinds of ways, the topology is retained. So what we want to know is actually only the connectivity. We're not so much interested about what the dimension is of these things. The same thing for the topology here of the low density areas, right? So that's one reason why we want to know that. Another reason is what we want to measure. Well, what cosmologists usually do is they take the mass distribution and they filter it with some filter on a certain scale, and then they look at the regions that lie below a certain density. For example, these are the 24% lowest, 50% lowest density regions. These are the regions 24% highest, 50% highest. And then you look at the genus of these surfaces. You measure the genus, that is the number of holes minus the number of components, and you look how it varies as a measure of the threshold. So this is the mean density. These are very low density regions, very high density regions. You see that it's very low first, then it goes up like this, peaks at 0 and goes down. Right? Now this is almost the signature of what we call a Gaussian distribution of matter. When it's non-Gaussian, that is on much smaller scales, or when this assumption of Gaussian initial conditions was not true, then you get actually a distortion of this map, and you see that you get more the peak shifting towards the right. That means that we have a sort of bubble-like cluster bubble-like topology. So you get this. And one of the things we have to realize, for those of the mathematicians here, by the way, is that cosmologists use this term for genus, which is basically the number of holes minus the number of connected regions, but that's not the proper definition. So you always have to take into account that the proper genus, capital G, is basically the cosmology genus plus the number of connected regions. That may cause quite some misunderstanding, actually. Now, yesterday we already heard that there is a much more solid way of basically inferring these various topological features or topological characteristics in terms of the Betti numbers, which are basically the rank of homology groups. Now, the Betti numbers can be formally defined as the rank of homology groups, and they are a complete specification of homology, where we basically concentrate on the connection between cycles and boundaries. So formally they are the rank of homology groups, but informally, and in cosmological context it's sometimes good to describe it like this, it's the number of p-dimensional holes of an object or a shape, right? P-dimensional holes, what can that be? Well, I see I get all kinds of interesting symbols, but it looks like I'm into astrology here, but I'm not. This is really Betti 0 is basically the number of independent components. Betti 1 is the number of independent tunnels, and Betti 2 is the number of independent enclosed voids. So that's the more physical way of looking at it, right? Now, for example, to give you an impression of these Betti numbers, what they can measure, and a more rich depiction than just genus, is, for example, the Betti numbers of a point is basically Betti 0 is 1 and the rest is 0. But when you take, for example, this torus, then you get that the Betti number 0 is 1, it's one object, but you have two 1 cycles, this one and that one, so Betti 1 is 2, and Betti 2, that's the number of holes, is basically 1, that's the interior of this, and so you have basically a whole way of specifying the different topological characteristics. So how to define this? Well, the topology can be defined by terms of cycles, and cycles are basically connections and can have different dimensions. For example, in this case, the one-dimensional cycle of around a torus, you get a cycle that is possible like this. This is a connection, but also you have one like that. And you can have a large number of them, but in the end, they all can be written in terms of these two cycles. That is, when you take all the cycles, you can basically make a group of p cycles and ask yourself what's the rank of that group, and that is then called the Betti P, the Betti number of that particular homology group of p cycles. In terms of three-dimensional objects, basically you have 3 or 4 Betti numbers, but Betti 3 usually in most circumstances is just 0, so they are 2. Now, how to measure this? That's the question. That brings us back again to the issue that we have a discrete number of points. And normally you could take a surface, but the surface is basically smoothed, and that's what we want to prevent. That brings us back to the issue of triangulations. So triangulations can basically be used to sort of approximate a given surface. Or in the case of, for example, the galaxy distribution, that's all that you have. You start with discrete points. I showed you already an example, the Delaunay triangulation, and we will use this Delaunay triangulation at all. So a triangulation is basically a conglomerate of various simplices. In this case, you see a triangulation of a sphere, and you recognize vertices, you recognize edges, you recognize faces, and all these kind of things. Now, if you take a surface and topologically you approximate it in the right way by a triangulation, then the topological properties are completely retained. They are homeomorphic. But it's much easier to measure your topology on the basis of triangulations. Why? Well, for that we have to go back to the Euler theorem, which basically tells you that when you want to measure the Euler characteristic of a surface, of an object, actually, in the case of a triangulation, any triangulation, it's simply the number of vertices minus the number of edges plus the number of faces. This is a very profound theorem. We will see it comes back all the time. It looks like something 19th century, but it is really coming back big in this whole game. And the Euler characteristic is, to some extent, what we want to measure also. Now, if we have a triangulation, we can use all this stuff. And we have a triangulation, we have the Delaunay tessellation. So you can prove that actually in a general d-dimensional space, the Euler characteristic is the alternating sum of the number of simplices. So I showed you the 3-dimensional, but you can go to any dimension, and this is always true. Right? So in that case, you have the multidimensional versions of lines and edges and all those kind of things. Now, when you look at this, perhaps you will not be amazed to recognize that there is a direct link with the same thing in terms of Betti numbers, right? Because you're talking about cycles. Cycles can be approximated by basically, for example, a loop can be approximated by 3 points, right? So that's a cycle in one-dimensional. So in the end, and that's the so-called Euler-Poincaré formula, O2 Euler-Poincaré, you can also find that the Euler characteristic is the alternating sum of the Betti numbers that you want to measure. The profoundness goes even further. Let me skip this one. And this is very interesting for us cosmologists these days, is when you look at surfaces And in the surfaces, you recognize the maxima and the minima and the saddle points. In other words, you use Morse theory to describe this whole structure of this thing. You could ask yourself, what's the Euler characteristic of the various surfaces? Amazingly, what you find, so for example, this is a minimum, these are the maxima, and these are the saddles. It turns out that the Euler characteristic is the alternating sum of minima minus saddle 1 plus saddle 2 minus maxima, etc. for d dimensions. So all these things, and they have all been considered in cosmological context, are intricately connected. And the way to go is via the triangulations. So we are going to measure the Betti numbers via triangulations. And in the end we can then get the genus, we get the Euler characteristic and all these things that we know in addition to the Betti numbers, because the Euler characteristic is just an alternating sum of the Betti numbers. So how do we do this? Now that brings us back to alpha shapes. A little bit longer than that, a few minutes. Alpha shapes are basically subsets of the Delaunay tessellation. So you take a Delaunay tessellation and you subsequently start to take subsets of the Delaunay tessellation and start to basically take out the simplices of the Delaunay tessellation that are within a given distance from the points. Let me go to this game to explain this to you. So this is the Voronoi tessellation, and look here at the Delaunay tessellation. So what we do then is we start with spheres around the points. This is one sphere with a certain radius. You see that only two spheres start to touch. There is only one Delaunay simplex here that is within this sphere, this object, right? Now I increase the what I call alpha radius, and look here. You see this one starts to touch too. So now I have two elements, like this. It's still a chain, it's still not a cycle. Now I increase the radius again, and now these two guys started to contact. Now I do it again. Now something here happens. See? Like this. I hope the next one it was the next one which had the trend. No, not yet. Yeah. You see, now a topological transition happened. Here, suddenly a connection happened here, a cycle, and actually there was a cycle, and immediately this whole thing is filled up. That's a topological transition. I now know that I include here a two cycle, or basically a surface, and I have an enclosed one cycle. So you can basically, as a function of scale, start to fill up your Delaunay tessellation. In the end, of course, you end up with your complete Delaunay tessellation and convex hull. The interesting thing is that here you have the resulting alpha shapes, so those simplices that belong to this, within this agglomeration of spheres, and from these things you can basically determine in the good old way the Betti numbers by measuring them from the triangulation. To this end you can use an algorithm which was devised by Edelsbrunner, which just calculates in a very ordered way the various cycles that are in these alpha shapes. And thus we get basically the whole range for different scales of the Betti numbers. So in view of the time, let me then show you, I have to proceed this to what this leads to in a cosmological context. Okay, so here are some results. This is a model of a distribution of filaments. This is a toy model. But you may wonder how, as a function of scale, do the different Betti numbers go? So here you have the Betti 0, Betti 1, and Betti 2 of that model, right? We can now try to study, as a function of parameters, the various, how these different curves go. So for example, here we have an evolving distribution which goes from wall-like to filaments to cluster-like. What happens in that case? In that case, you get, for example, in the case of the Betti 2, an evolving Betti 2 curves, and you see at various stages different peaks. And these different peaks probe the different structures that we see. So there is more information there. We can also plot, for example, Betti 0 versus Betti 1 versus Betti 2, and you look as a function of scale how it runs. This was the initial condition, and you see as time proceeds it's moving towards that direction. That is more information than just genus. It's a lot of extra cosmological information. Then, in the end, and that's where I want to conclude, we can try to see whether we can use this to get out real cosmological information. So what we did here is to apply this to several models of cosmic structure formation containing different different kinds of dark energy, and see whether we can see the differences between these different cosmologies. So these are the different alpha shapes for different values of alpha. This is the evolving Betti 0, Betti 1, and Betti 2, and as time proceeds you see it shifting away towards larger and larger scales and the peak becoming smaller. This is Betti 0, where we see basically that the number of voids, large voids, is basically diminishing with time, and the number of large voids is growing. So what we effectively see is the small bubbles merging into larger and larger bubbles. And then finally, we can see for the different models of dark energy, what you see here is the 3 different models of dark energy, and you see that the Betti 0, the Betti 2, and the Betti 2 and the Betti 1 are slightly different, even at the present cosmological epoch. And that's what we exactly wanted to have, because at the time one of the big questions is, what is the nature of the dark energy, and is there any measure in the large-scale distribution of matter that allows us to determine this? Now, we have these different models where this dark energy is evolving differently, and in all cases, although by eye you could hardly see the difference between the different models, here you see basically 2 different models, and you see the distributions are almost the same. The Betti curves have indeed been able to pick them out. Now this is a preliminary result, but the prospects for this kind of description of the large-scale distribution is certainly very promising. What I didn't get to yet is the fact that we can sort of formalize also the multi-scale character of this in terms of persistence diagrams. And there the sensitivity is even more outstanding, but that is work in progress, and I hope to report that at some other occasion. Okay, thank you very much.
Well, thank you very much for this fascinating talk. We're running a little late because of the technical problems before, but we have time for a few questions.
Does it mean anything about the universe, or it just tells us something about the tools that you use? I suspect that if I randomly generate 1 billion points in the sphere, I completely uniformly at random, and I start applying all those tools, I'll find some structure. How do I know that this structure is just not just an artifact of the tools that I use, but it really tells me something about the world.
Well, the common way of going around in cosmology is basically to normalize it with respect to structures that we know. So, for example, slightly before this, I showed you an artificial model, which we call Voronoi clustering models, where we know exactly what we put in. It's a toy model, right? So there we basically measure the outcome of these various measures and whether it makes sense. For example, finding voids, right? Now, we know the number of voids we put in there. They have one particular scale, and the question is, do I find them or not? Same with filaments. And once we have ensured that the method really gives this, then we say, okay, now we are okay. Now we can go to the more complex world where we have the full multi-scale character, etc. That's the way we work. If you want to say, are you 100% sure? No, I cannot be, because the structures are so very complex, right? We are describing very complex structures of which we do not have precise predictions. The only thing is that we can test, like I said, in this way. Another way I can, for example, say is I claimed that we pick up this multi-scale character, right? That we had these by this geometric method, that we picked up all the features that are there, and that we have the complete rendering of the density distribution. So what did we do? We took some artificial models, very well-defined fractal models, where we knew exactly the amount of clustering, where we knew exactly the different fractal dimensions, and we got them out 100%. I cannot say more. Okay?
So I'm worried that Shai will answer, so I will rather take another question now. I think you were first.
You said that the main underlying entity is a web of dark matter. How strong is the assumption that the visible light of the galaxies is really, say, proportional to the density of the dark matter? Or do you have any model?
That's a very deep and profound question. And that has been bothering cosmologists for a long time, because we don't understand how galaxies are forming. So how do we know for sure they basically are sampling this? Now, in the last 10 years, we are also succeeding in measuring the distribution of the dark matter by a technique which looks at the bending of light as it proceeds through the universe, which is called lensing. This allows, this bending of light is only by mass. So you're not measuring light, you're measuring the mass. And you can reconstruct, basically, fully, the density distribution in the dark matter. Now, it's much more gross, or how do you say, it's much more rough than what I showed here. But we do now have maps of the dark matter distribution. And for the first time, since the last 2-3 years, we can compare. And we are a little bit amazed to find out that the galaxies are indeed a very good tracer of the dark matter. Tells more about the galaxies than about the dark matter.
Okay, so there were 2 more questions. I think we cannot take more than that, and maybe with brief answers, and if you need more detailed answers, you come and see him afterwards.
Okay.
My question might be related to the previous question. So, I mean, you described sort of the universe as an evolving system, pattern formation, and we're moving towards structure. So how do you reconcile that with the second law of thermodynamics? So what you're looking at can't be a closed system. Is that now where the dark matter comes in? That it's like a huge heat bath.
Another very deep question. What's happening to the entropy? The universe is constantly creating entropy by its expansion. So there is no problem with the second law of thermodynamics. It's a very deep question. We can maybe discuss it later.
Okay.
So, as you get out further into the universe, you're going further back in time. So when you try and look at this web structure, bits of it happened at different times. So do you have to deal with that in the modeling? Because you'd be looking at one end of it, and that's now, and the other end is 30 billion years ago, and we might expect it to be a bit smoother at that point.
Yeah.
This time it happened.
Yeah. So our methods have an intrinsic smoothing by themselves. So the tessellations that are underlying all these tools adapt themselves to the distribution of points themselves, right? So the scales you get automatic. When the scales were different 10 billion years ago, the tessellation will show that. Now, I have to be fair to say that we hope that in the coming 10 to 20 years we are going to have the maps from the galaxy distribution out there, but we're not there yet. It's still pretty local.
Okay, so thank you very much.
Okay.